All right, this talk is going to start on time for two reasons. One, I've got a lot of material to cover, and two, it's a talk about time, so let's be ironic. And also, because I've got a lot of material to cover, I'm going to ask you to keep your questions to the very end because with questions, this is about an hour and a half talk, and I've only got an hour, so questions at the end. And also, if you don't get your question in at the end, I love to talk about this stuff. I'll be here all week. Just catch me in the hall and ask your questions in if you get crowded out at the end of this talk. So this library, everything you need to know about this library it's in standard header chrono, and everything that I discussed today will be in namespace standard chrono. I won't always have that explicitly on the slide because it's a mouthful and it's a lot to write, and it means it wouldn't fit on the slide. So I'm going to start with talking about the motivation about why you'd want to use chrono in the first place, and then I'm going to talk about time durations and points in time clocks and wrap up with some examples. So the first thing that some people ask when they first start looking at a time library is, why do we need something fancy like chrono? Can't you just use an int for the number of seconds since 1970 or what have you? It worked forever in C. And you see something like this. Well, actually, you see sleep 10 in your code, and the 10 is ambiguous. Is that sleeping for 10 seconds, 10 nanoseconds, 10 microseconds? Nobody knows. But if you've got a time library, you can write something like 10 ms, which means 10 milliseconds. It's much more readable. You can tell exactly what this is supposed to do. Now, admittedly, for ms, you need C++14, not C++11. I'll be mainly talking about C++14 here, and the parts that do have a limitation to C++11, I'll try to elucidate those. So your code becomes much more readable when you've got a typed system, a strong type safety system for your units. And in general, using an arithmetic type to represent a duration or a time point is just intrinsically ambiguous. So chrono is all about helping the compiler help you find your logic errors at compile time. And it does this by making distinct types, distinct concepts. So I'm going to start out with time durations. And a time duration is just a period of time. It could be 3 seconds, 3 minutes, 3 hours, what have you. And I'd like to start out with our very first duration unit, seconds. Now, seconds is a very trivial type. All its special members are trivial. It's basically all it has is it's a long inside of it. It's just a wrapper around a long or a signed 64-bit type. It's very simple. Here is how you can visualize it. It's just a class. It's got a long in it. It's default constructible, trivial special members. It's very, very simple. To construct a seconds, you can construct it like this. If you don't have initializer on it, it's just like long. You get an uninitialized duration. If you want to zero initialize your duration, you can add the curly braces or the parens, and that will zero initialize your duration. So not only is it just like a long, you don't have to worry about it if you've got say a vector of seconds, and your vector is 1,000,000 long. You don't have to worry about that vector going through and zero initializing every single one of those elements unless you ask it to. So the one thing that you can't do with seconds is implicitly initialize it from an int. For example, if you say seconds s equals 3, this will not compile. Now, it turns out that in chrono, it's almost as important what it won't do as what it will do. And this is all about catching your errors at compile time. And that'll become clearer, at least I hope it'll become clearer as I talk more about it through this talk. But of course, sometimes you need to say 3 seconds. And this is how you do it. You just say seconds, and seconds is in namespace standard chrono. That's not shown here. And you can use the curly braces or parens, and you give it some integer. So here's how you'd say 3 seconds. Very simple. Unfortunately, printing them out is not as easy. It should be. There's no good reason why it's not. But I'm presenting a library tomorrow that will fix this problem. You should consider this part a bug. To print out a duration, you actually need to use this member function called .count. And all .count is it returns that 3 that's stored in the long inside. So durations are very simple and they're very observable. If you want to get that long out, it's easy as .count. And so here I've also added the S so that you can see that, yes, I'm printing out 3 seconds. So far, very easy, very simple. Now, here I'm writing a example function called f, and all this function's going to do is print out the value. In general, you might have a function that does arbitrarily complex things with your durations, but just for the purposes of this talk, our example function is going to do nothing but print it out. Now, if you call this function with an int, you get an error, f of 3. And this is a very important error. Again, I hope I'll be coming back to this again and again over the talk just to emphasize it. If you call f of 3, since 3 won't implicitly convert to seconds, you get this compile time error. Now, if you think about this, if you didn't see the function f above, all you were looking at in your code was f of 3, you might look at that and say, well, I know it's a duration, but is it 3 seconds? Is it 3 milliseconds? Is it 3 nanoseconds? You wouldn't know. So that's one of the reasons that it's very important for this to not compile. If you want this to compile and mean 3 seconds, then you would do it such as this. You'd form seconds 3 explicitly. And that's perfectly fine, and this will run and print out 3s. In C++14, you can actually say 3s. S is a user-defined literal, and you can form 3 seconds that way. It's the exact same efficiency. It means the exact same thing. It's just a little bit more readable and concise. You can form an L value of seconds type and pass that. Same thing, same efficiency. You're literally just passing longs around, but it's just wrapped up. So additionally, you can do subtraction and addition with your durations. There's the plus equals, the minus equals. You can say seconds minus seconds, seconds plus seconds, and it all just works except this very bottom line. If you say something like x plus 1, again, you get a compile time error. Why? Because the 1 is ambiguous. You don't know whether that's a minute or an hour or a second or whatever. So the library will refuse to compile that. Additionally, you've got all 6 of your relational operators, equal, not equal, less than, greater than, et cetera, et cetera. So here I've written a function, and I've got my argument D, and I'm comparing it to some global or whatever, some faraway code called time limit. And you see my time limit also has type seconds because of the S on the end here. So very easy comparisons, things just work. And if we call this like so, then in this example, it would print out of time 3s. Now, if we accidentally forgot to make our time limit of type seconds, say we accidentally made it an integral type, this would again not compile because 3 seconds is less than or equal to 2. 2 what? It's ambiguous again. So you can't compare seconds and ints. You can only compare seconds and seconds, or more generally seconds and durations, and I'll get into that. So as long as you have your units correct, things just work. So one of the things that people worry about well, how much am I paying for all this? So what I'm going to do here is create a function that does nothing but add 2 seconds. And I'm going to do it 2 ways, one using the chrono library, and the second way using basically C. I'm going to take a couple of longs, add them together, and instead of timing this, the operations are so quick that it's tough to get accurate timing on them. So instead, to look at the performance, I'm going to compile these using Clang optimized -03, and I'm going to show you the assembly listing of both of these functions. Now don't worry, you don't have to be an expert at reading assembly to get the point that I'm about to make. So compile both of these, look at the assembly, and here's literally what each one of them generates. This is the entire operation, and the assembly code for both of those functions is exactly the same object code, except for the name mangling at the top. And this is, again, for release configuration. For debug, you would get, it wouldn't inline and stuff like that, so you would get different object code generation for the two functions for debug mode. But for release mode, there's absolutely zero overhead here, the exact same object code. So what's the range of seconds? Well, it's unspecified. It's different for each platform, but you can query it. Seconds has static min function and static max function. You can get those. And it's chrono has currently three separate implementations. Two of the authors are actually here in the room. I did one of them. Stefan did a second one. And on all three implementations, the range on seconds is plus or minus 292 billion years. That's a little bit older than the age of the universe. So if you overflow, you've got problems beyond just overflowing seconds. You've got some serious something wrong going in your application. The intent here with having the range so large is so that you don't really have to worry about range checking that much with the chrono library. It intentionally has very large ranges so that if you overflow, it's going to be something obvious and very bad going on. You don't have to check every single little operation to make sure you're not overflowing plus or minus 292 billion years. So seconds is just a wrapper around the integral type, long. Is this a big deal? And I claim, yes, this is a very big deal, and the rest of the talk will hopefully convince you of why it's a big deal. So one of the things you might imagine is, let's say you're in charge of a large program, maybe a 1,000,000-line program, maybe 100 million lines of code. And you've got all this timing code through it, and it's all based on seconds. And somebody comes through and says, we need to start trafficking in milliseconds. Can you make that happen? In a small program, it'd be easy. You just substitute in seconds for milliseconds, double check everything, run it through your unit test, and you'd be done. When you've got millions of lines of code, if anybody of you have handled code that big, that can be problematic. So chrono also has this type called milliseconds. And milliseconds works just like seconds. It's just a wrapper around a long. It's got all the trivial special members. About the only difference is its range is only 292 million years instead of 292 billion. Still have plenty of range. So we just search and replace our code and replace seconds for milliseconds? No, that would be a dangerous way to do things. Chrono allows you to do something that is much, much safer than that. You modify a small piece of your code at a time, just porting that one piece of code from seconds to milliseconds, and then you recompile and retest. Don't modify your entire 1,000,000-line program at once. That would be a disaster. So to show you what that would look like, let's look at our tiny little function that does nothing but print out its duration. Let's pretend like this is some small piece of code in your very large program. Let's port this, and then we'll see how the rest of the program reacts to our porting. So we go through and we change seconds to milliseconds, and because we're printing out, we change the S to MS so that we get a nice printout. What does the rest of the code do, the rest of our large function? I think I'm blocking my signal here. So before, if we called f of 3, it didn't compile. Now when we call f of 3, it still doesn't compile. Now let's just think a minute. Let's pretend it did compile when we used to have f taking seconds. Then this would have meant, call f with 3 seconds. If it compiled again now, the meaning of this function would have changed. And now we'd be calling f of 3 milliseconds silently. That would be a runtime error. It'd be a change in behavior that would be silent. So this is why it's so important that ints not implicitly convert to durations. Now, if we call it with if we look at our calls with f of 3 seconds, in each case, no change is needed. The call with 3 seconds will implicitly convert to 3 milliseconds and print out exactly what it should, 3,000 milliseconds in every case. So the rest of the program continues to work. Now there are cases where it won't work, but those cases will refuse to compile instead of compiling and creating runtime errors. So in general, port your small piece of code and the rest of your program will either compile and do the right thing or it won't compile. And you'll get error messages that will hope you lead you to how to make things compile and make them compile correctly. So let's look at our second example, our little bit more complicated example function, where we can compare it with a time limit. Let's port this. We change seconds to milliseconds. We change our output from S to MS. What happens with this? Well, one of the really interesting things with this is this function is referencing this faraway global, this time limit thing. Did we have to change that? And the answer is no, not at all. That can stay seconds. Milliseconds will compare to seconds, and it will always get the right answer. And it won't even cost you anything at runtime. The compiler says, oh, I see I've got seconds here. I see I need to compare it to milliseconds here. This is a compile time constant. I know that at compile time, I will convert that 2 seconds to 2,000 milliseconds and then do the comparison. Zero abstraction overhead. So things just continue to work properly. And at our call site, we call this with f of 3 seconds. We don't need to change that. And we get the exact same behavior, except now it's printing out 3,000 milliseconds instead of 3 seconds. So things just continue to work. So the chrono library knows about the relationship between milliseconds and seconds. It knows it has to multiply seconds by 1,000 to get milliseconds, or divide if you're going the other way. One of the poor practices I often see when people start using chrono is they get the number out with the dot count function and they start doing their conversions manually. They'll multiply by 1,000 or divide by 1,000 or what have you. Don't do that. Chrono can handle all the conversions for you. Don't code your conversions manually. If you're doing that in 100 places over your 1,000-line or million-line program, odds are you're going to get one of those places wrong. You're going to multiply by 1,000 when you should have divided, or vice versa. If you always let chrono do your conversions, chrono will never make that mistake. And the code that chrono generates will be just as efficient as if you'd hand-coded that times 1,000 or divided by 1,000. And to demonstrate that, let's do our compile time test again. I've got my function, and I'm going to convert seconds to milliseconds, and I'm going to do it 2 ways. Once with the chrono library, and we have an implicit conversion here from seconds to milliseconds, and then in the caveman Neanderthal sort of way, where we multiply by 1,000. Compile both of these, optimizations on, the exact same object code gets generated, except for the name mangling. So there is really no cost at all, no runtime cost to using the chrono library. So chrono allows you to migrate from seconds to milliseconds, a small piece of code at a time, and code across such a transition that hasn't been ported yet will either be correct or it won't compile. And even if you have a context where you need to do mixed mode arithmetic, you need to start adding milliseconds to seconds or subtracting them, things will just work. If you, here I'm adding seconds and milliseconds and we get 2,003 milliseconds, we pass that to our function f and it'll print out 2,003 ms. So mixed mode arithmetic works just fine. So if it compiles, it's working. Don't worry. Now if it doesn't compile, I think I skipped a slide there, I'm sorry. Let me backtrack a little bit, because this is important. If it doesn't compile, Don't escape the type system with that .count member function and do it yourself. Instead, try to understand why it didn't compile. It didn't compile because chrono's trying to tell you that you did something that's not right, and it shouldn't compile. So that's another mistake that I see all the time is people using chrono, and they're so happy that they've ported to chrono, and then they need to do something and they can't get it to compile. They get frustrated and they say, oh, I know I can just get the number out with .count and multiply by 1,000 or what have you. Please don't do that. If you have to, just email me and I will help you fix your code and we'll both learn. So the one exception to that is if you're interfacing with legacy code, and unfortunately cout or streaming out is legacy code at this point. If you're interfacing with legacy code that doesn't know anything about chrono, you might have to use .count for that. So in general, so far we've only talked about what I call lossless conversions from seconds to milliseconds. If you have a certain number of seconds, you can always represent that in milliseconds, assuming you don't go over the 292 million year boundary. So the milliseconds can always exactly represent the number of seconds you had. And so all lossless conversions are implicitly allowed to happen, as we've seen. However, when you go the other way, try to convert milliseconds to seconds, that's a lossy conversion. If you have, for example, 3,400 milliseconds, you can't exactly represent that in seconds. So that conversion, the chrono library doesn't allow you to do. At least it doesn't allow you to do it implicitly. It says, wait, are you sure you want to do this? Because you're going to lose information. Now, sometimes that's exactly what you need to do. You need a bigger hammer sometimes. So there's a function in the library called duration cast. You supply it as a template parameter, whatever destination type that you need, and then it will do the truncation for you. It'll do the divide by 1,000 essentially. So if you duration cast to seconds, 3,400 milliseconds, you get 3 seconds out of that. So it's also important to understand that duration cast means truncate towards 0. Now, if we're looking at positive durations, that's always truncate down. But if you're looking at negative durations, like negative 3,400 seconds, that's truncate up towards 0 to be negative 3 seconds. In C++17, you'll get new rounding modes. There'll be floor for always truncating towards negative infinity, ceiling for always truncating towards positive infinity, and round for truncating towards 0 with towards even on a tie. And if you absolutely need those before C++17, my website has them. And it's this much code, you can just copy paste it. There's no copyright issues or anything like that. So, in summary, only use an explicit cast, only use the duration cast or the ceiling or the floor when the implicit conversion won't work. If the implicit conversion compiles, it will be exact, and that's what you want to do. And then if it doesn't compile, you can make the decision, okay, I see that I'm doing truncation error here, and you can decide, this is your chance to think about, should I truncate towards 0, should I round, should I truncate towards negative infinity, what have you. Now, so far, we've only talked about seconds and milliseconds. We can handle more units than that. We have a few more units than that in the chrono library. We've got everything from nanoseconds to hours. Now, everything that I've told you about seconds and milliseconds is exactly true for all these other units as well. So there's not that much more to learn. They all interoperate with each other exactly as I've described with the seconds and milliseconds. They'll implicitly convert from coarse to fine. And if you need to go from fine to coarse, you need to use duration cast. And they all work together seamlessly. So let's take a look at a few examples. Let's say we rewrite our trusty f function here in nanoseconds. Now I can do mixed mode arithmetic. I can add hours and microseconds. Pass that to our f. That will implicitly convert. It'll add the hours and microseconds together, and that creates a sum of microseconds. And then that temporary sum gets implicitly converted into nanoseconds as it's being passed to f. and it prints out this outrageously large number of nanoseconds. So we're looking at relatively complex code here. I mean, it's not rocket science, but it would be easy to get wrong if you were doing all these conversions by hand. And the code is very clean looking, and it's guaranteed to work. It will always get the right answer. So a lot of people start thinking, well, gee, using long longs for all my time durations, that's kind of expensive. This is overkill for my application. Say you're building a TRS-80 emulator or whatever. I only need 32-bit seconds for whatever reason. Well, of course, that's going to overflow a lot easier, but if that's what you need to do, if that's what you want to do, Chrono's got you covered there. There's this template in Chrono called duration, standard Chrono duration, and as its first template parameter, it takes what I call the representation. And you can pass into that representation a 32-bit int, and this is just this is the same thing as a type def for those who aren't used to the using syntax of C++ 11 and 14. So this creates a type def called seconds32 that is a 32-bit seconds representation. And this seconds32 will be a first-class member of the Chrono library. It'll interoperate with milliseconds and seconds and hours and nanoseconds in the exact same way I've already described. So you can create your own seconds using int32, and hopefully that will talk you into using it even if you're building a TRS-80 emulator. Some people still complain. They say, well, I really meant unsigned. Okay, you can stick an unsigned int32 in there as well. Some people still complain, well, since it's only 32 bits, I actually need overflow protection. Fine. There's plenty of safe int libraries out there where you can find one or build your own. You can wrap your int32 up into whatever safe int library you want and pass that in as the representation, and Chrono will still deal with it. All the arithmetic it'll do on this safe int32 type. So you can, there's a lot of flexibility here. You can pass almost anything you want into Chrono as a representation. And as long as it's emulating an arithmetic type, it'll just work. Now I used arithmetic type there on purpose. You can plug in any arithmetic type in for this representation or an emulation of an arithmetic type. And yes, that means even floating point types. So if you want to have a seconds that can represent fractions of a tick using a float or a double, if that's what you want to do, knock yourself out. And there's some interesting facts about using floating point types for your representation. Recall that if I said that if your conversion is lossless, i.e. if there's no truncation error, it should be allowed to happen implicitly. Well, if your destination is a floating point type, there's never going to be truncation error. There might be round off error depending on the precision of your floating point type, but there's never truncation error. So if the destination is a floating point type, the conversions are always implicit. So here I'm adding 45 milliseconds and 63 microseconds, and then implicitly converting that to a floating point second, and it just works. It compiles and it prints out 0.045063, just like you think it should. At this point, you might be wondering, well, what I really want is generalized representation on something that's not seconds. Say, for example, milliseconds. Can I do that? Of course you can. This is Chrono. You can do anything. So here's how you might do this. Here's a template type def. There's a second template parameter to this template duration that takes what's called a ratio. And in a few slides, I'll go into a little bit more detail about what a ratio is. But there's a ratio called milli. It's in the standard namespace. And so here is how we can make a type of any representation we want that's always going to be milliseconds. And just to demonstrate it, here's a millisecond based on float. And if I put in the same expression we had on the previous slide, now it continues to work, but instead of 0.045, blah, 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 it prints out 45.063 milliseconds, which is, of course, exactly right. So you've got a lot of power and a lot of flexibility here to do really almost anything you want. So we're going to dive a little bit deeper here, and I'm going to explain some of these things that I've been showing you. The standard actually specifies seconds, milliseconds, microseconds, and nanoseconds exactly like this. These are specializations of this template called duration, and they have a representation of signed integral types that have at least this many bits in them. Now, you don't have to memorize those number of bits. What this means in practice is that if the number of bits required is over 32, the implementations are going to be using a 64-bit signed int in here. So all of these would be using long or int 64t or what have you. And the second template parameter, there are predefined or standard-defined ratios called nano, micro, milli, and several others. And so those are defined for nanoseconds, microseconds, milliseconds. And the duration template itself defaults this second template parameter to a ratio of 1/1. So let's look a little bit more about what ratio is, so that's not such a big mystery. Ratio is a compile time fraction. That's all it is. It's a template. It takes two signed integrals representing the numerator, denominator, and it has const expr members, numerator and denominator, abbreviated num and din. And all ratio does is it takes its template parameters, reduces them down so that the most compact, reduces it down to lowest terms. And then you can use this to represent your compile time fraction. In addition, the standard specifies that we have these predefined ratios. This is 1/1,billion, 1/1,000,000, 1/1,000. So these are just really the SI units, milli, micro, and nano. So the duration template uses these ratio classes to do these conversions that I've been telling you about. So here's our complete definition of all 6 chrono durations. And it uses these predefined ratios for the first 3 periods. Here I've explicitly put in ratio of 1. This just means 1 second. It's the fraction 1/1. And then for minutes, ratio of 60 seconds per minute. For hours, ratio of 3,600 seconds per hour. And it's these ratios that make all the conversions work. The compiler will say, oh, I see hours has this ratio and nanoseconds has that ratio. So I divide these 2 ratios at compile time, and that's how I figure out how to convert hours to nanoseconds. So I got to admit, I lied to you a little bit earlier in the talk when I said seconds was this class called seconds that's got an int long in it. Seconds is actually a specialization of this class duration that is templated on rep and period, and it stores only the rep. The period is not stored. It's simply part of the type. So rep is the only data member, so I didn't lie much. It really does look like a class called seconds with a long in it, except it's a specialization of a template called duration. Now, one of the nice things about duration, it has these nested types called rep and period, so that if you get a duration, say that it's generic, and you don't know what it is, and you want to inspect it, you can say, if it was milliseconds, for example, you can say milliseconds, period, that's the ratio, get the numerator out of it, and that's going to be 1. And you get the denominator out of it, that's going to be 1,000. If you want to see what the representation type is for the milliseconds, it's not specified to be int 64t, but in practice, that's exactly what it is. So you can, these are all very observable. All of the compile time characteristics of all of your durations are very observable. So now that we know that this is how durations are made, you can build your own custom durations. Let's say you've got a game application that you're working on and you want to measure frame rates at 1/60th of a second. Here is how you build something that means 1/60th of a second stored in a 32-bit int. And let's say, for example, we still have our function f that just prints out its duration, and let's say we're taking the version that uses floating point milliseconds. We can use our custom duration called frames, send in 1 frames to this, and it will automatically convert to these floating point milliseconds and print out 16 2/3 milliseconds because that's what the conversion happens to be. You don't have to do any of this math itself. The only math you had to do is specify this 1/60th right up here, which means 1/60th of a second. You can even do mixed mode arithmetic between your custom duration and the standard supplied duration. It turns out that 45 milliseconds and 5 frames are 128 1/3 milliseconds. Who knew? So this last one is a little bit interesting, and I'm going to do a deep dive on this to show you all the gory details about what's going on under the hood to make this happen. And I'm going to use a pseudo syntax here. Everything inside square brackets is always compile time information, which means it's never manipulated at runtime. All the computations involving inside square brackets always happen at compile time. So here I'm just using this syntax to represent milliseconds, this syntax to represent our custom frame duration, 1/60th of a second. Notice that the representations are different. The first thing that happens is the compiler says, oh, I need to add these two. That means I need to bring them to a common type, a type that I can convert both of them to losslessly. So the compiler figures out that it needs to make both representations signed 64-bit int, and it needs to change the period to 1/3000, which is the least common multiple. It's using essentially the same stuff you learned in 3rd grade, 4th grade, whatever it was. This is how you add fractions. Your compiler, the chrono library, knows how to do this at compile time, and this is what it does. Once you've done that, you just do the problem in the common type, multiply 45 times 3 and 5 times 50, you get 385 int 64Ts of units 1/3000. And then the last step of this was to convert it to floating point milliseconds. And so you simply divide everything by a floating point 3 and you come up with 128 1/3. So it all just works, and it all works implicitly, and most of it is working at compile time. And to demonstrate that, if we had some function called test up here that took runtime arguments, x and y for milliseconds and frames, this is the assembly generated. And the thing to really notice here is what's not there. You don't find any calls to greatest common denominator in this call because they happened at compile time. They don't exist at runtime. All you've got at runtime is multiply by 3, multiply by 50, you add them together, and you divide by the floating point 3. That's the only stuff that happens at runtime. So this is very efficient. If we had to do all that finding the common type, finding the greatest common denominator, those fractions at runtime, this would turn into a fairly expensive library. But it's not an expensive library. So I know, especially with that deep dive, I've been hitting you with a lot of information. You may feel like you've been drinking from a fire hose, but there's more. I'm not finished yet. However, before we go on, I want you to know that, remember back in the beginning of the talk when I said there was just seconds and maybe just milliseconds, and they were nothing but long longs wrapped up in a class? All of this fancy stuff that I've been talking about, the frames, the floating point milliseconds, and all this stuff, it's all there only in case you need it. And if you don't use it, you don't pay for it. You can pretend it doesn't exist at no cost to you. So it may seem like a contradiction, but this is a simple library. It's only as complicated as you need it to be. Seconds is to this duration template type just the same as string is to basic string, char traits, char, allocator char. A lot of times you just use string and you don't think about the fact that it's a specialization of this very powerful, very flexible template. Think of seconds the same way. Don't worry about the fact that it's a specialization of this powerful, complicated template called duration. It's just a long long wrapped up in a class. So this library lives and dies by converting one type to another. If the conversion is lossless, that conversion can be made implicitly. If it's lossy, you need a conversion function such as duration cast. And if the conversion is dangerous, such as converting an int to a duration or a duration to an int, there's very explicit syntax for doing that. So if you make a change in your million-line code, and it's a reasonable change that doesn't involve an explicit conversion or dot count, and if you are only using implicit conversions, you can have some confidence that you haven't introduced a bug in your code, because chrono will catch silly bugs that you might have made otherwise. So in all of your conversions, use the weakest type conversion that you can. Use implicit conversion if at all possible. This is another mistake that I see beginners make. They say, oh, duration cast, that's how I should make all my conversions. No, use duration cast only in those places where it won't compile, only in those places where you need to specify truncation. The reason for that is making a lossy conversion is a source for errors. Maybe you rounded down when you should have rounded up or whatever. If every single one of your conversions is hiding behind a duration cast, you'll have a lot more conversions that you need to debug through. But if only the lossy ones are decorated with duration cast, then you've got a lot easier debug job to do. So use implicit conversions everywhere you can. If it compiles with implicit, use it that way. Use duration cast if you need to specify a truncation. Try not to use dot count at all. Last resort, use the dot count. And for example, if you need to stream the duration out to a file or what have you, you'll need to use dot count. So that's durations. Now we can talk about points in time. Now don't worry, everything you've learned about durations will help you in learning about time points. A lot of that knowledge will carry through. There's not that much more to learn. So a duration such as 10,000 seconds means any 10,000 seconds, or if you prefer, 2 hours, 46 minutes, and 40 seconds. But there's this thing called time point, and just as an example, I'm going to throw system clock at you. A time point based on system clock with 10,000 seconds in it doesn't mean 10,000 seconds. It means this date here, 1970, New Year's, 2:46 some odd in the morning. So they both have 10,000 seconds. They both have the same representation. If you were to look at the binary representation of a time point and a duration, they would look identical in the debugger. But they mean very different things. One means any 10,000 seconds. The other means this point in time. So there's a time point templated class. This is exactly what it looks like. I'm not lying to you this time. The first template parameter is going to be a clock, and I'll explain more of what clocks are in a minute. They're not complicated at all. And the second template parameter is a duration that defaults to the clock's duration nested type. And the only thing that gets stored in a time point is the duration itself. The clock is not stored. And a clock has these nested types, clock and duration, so that if you get one generically, you can inspect it at compile time, find out what clock it's based on, what duration it's based on, and from the duration, then you can get the representation in the period, numerator, denominator, all very inspectable. And as I said before, time points and durations can have the exact same representation, they just mean different things. So when it comes to arithmetic, time points are very similar to pointers. They can be subtracted, and the result is a duration. But time points can't be added. Tomorrow and today are valid time points. Coarse ones, but they're time points. And today plus tomorrow makes no sense whatsoever. But tomorrow minus today is a duration. It's a day. So it makes perfect sense. And you can also add a duration to a time point, or you can say a time point minus a duration. And this is all a 100% self-consistent algebra that's checked at compile time. Again, chrono's trying to find all of your errors at compile time. If you accidentally add 2 time points, you'll get an error message. Might not be a pretty error message, I'll warn you, but it'll be an error message. It will not compile. So time points, since they have a duration in them, you have time points of different coarsenesses or different durations. And so they convert just like durations do. If you've got a time point based on seconds, and say it's got 5 seconds in there, just as an example, and another time point based on milliseconds, they'll implicitly convert, and that duration inside the time points will implicitly convert from 5 seconds to 5,000 milliseconds. Now, if you need to go the other way, like duration cast, there's a function for that. It's called time point cast, and that will allow you to convert from a fine precision time point to a coarser precision time point. And the C++17 rounding functions that I mentioned earlier, floor, round, and ceiling, are also all available for time point with the exact same spelling: floor, ceiling, and round. So use time point cast when you want to force a truncation error. Use implicit cast as often as you can with the time points. And you can explicitly force a more dangerous conversion from duration to time point with an explicit conversion syntax. Or if you want to go from time point to duration, there's a member function called .time since epoch, which just gets the duration back out of the time point. You should view that with the same skepticism that I've talked about with .count. It's a dangerous conversion. You don't usually want to do it, but sometimes it's necessary, and this is how you do it. Just be careful, that's the dangerous part of the library. So clocks. What is a clock? A clock is a bundle of a duration, a time point, and a static function to get the current time. So this is what some generic clock would look like. It would have all these nested types in it, so you can get the duration out, the time point out. If you want the rep and period, there's convenience type defs for that. There's a constexpr bool in it called isSteady. If isSteady is true, that means the clock can't be adjusted. It just runs. If isSteady is false, this is a clock that can be adjusted, say, for example, by a network time protocol server to correct for leap second events or something like that. So every clock has a time point associated with it, and time points from different clocks are not interoperable with each other. So for example, just trust me that there's two different clocks here named system clock and steady clock. And if we accidentally try to convert time points, a system clock time point to a steady clock time point, you'll get a compile time error. These two time points are not interoperable at all. Now what this means is that it's safe to use different clocks and their time points in the same program, because if you accidentally mix them, you'll get a compile time error. So, hope I haven't run out of batteries on my clicker here. It's interesting. So every time point's associated with a clock. Time points with different clocks don't convert to one another. And the library supplies, here I'm listing really only two. The library supplies 3 clocks for you, 2 of which are actually useful. It supplies system clock and steady clock, and then high resolution clock is a 3rd clock that it specifies, but the standard allows that to be a type def for one of the other 2. And in all 3 implementations, it is a type def for one of the other 2, but the different implementations type def it to different things. So my advice is, don't bother with high resolution clock, just choose system clock or steady clock, and that way you know exactly what you're getting. Now you might now be asking, well, how do I choose between these 2? So if you need a time point that relates to a calendar or a time of day, the time that the clock on the wall says, you have to use system clock. Only system clock has a relationship to any calendar at all. Steady clock, on the other hand, is just like a stopwatch. It's great for timing things, but there's no way you can get the time of day from a stopwatch. So steady clock for timing and system clock for getting time points that you need to store somewhere and read back in and still know what they mean because they're convertible to a calendar. So whatever clock you choose, you can get its nested time point like this, and you can get its the current time just like this. So very simple syntax. And chrono works really well with auto. People get very tired of saying clock, colon, time point, and that sort of thing. So this also works, and this is usually the way I write it myself. Don't have to repeat anything, and it's very simple. So let's look at some more examples. Here's how you might time a function. You just call steady clock on either side of the function, subtract them. Now, you don't always know what that nested duration is for those time points. You could find out if you wanted to at compile time, but here I've said I don't care what the nested duration type of that clock is. I want my answer in nanoseconds. So I just convert it to nanoseconds, use the dreaded dot count to print it out, and there I have it. If I wanted to do something else, say print it out in floating point seconds, that's just as easy. Or I could use duration cast and convert it to milliseconds. A lot of flexibility here. You can print it out in whatever units you want. The main point is that you should choose your units and explicitly convert to them so that you know what units you're getting printed out. The mutex functions have a trilock, a timed trilock, if you will. You can wait for a duration. In this example, I'm waiting for half a second, 500 milliseconds. You can also wait until a specified time. So for example, here I'm saying, okay, now plus 500 milliseconds, which is the exact same thing. But you might have a function where you call now at the beginning of the function, and you want to wait at the end of the function for now, the now plus 500 milliseconds. And it's difficult to know how long the function took between the time that you started the function and the time you started the wait. You don't have to take care of that, and that's why it's very handy to wait on a time point sometimes instead of on a duration when you need to take some other execution time into account. You can write your custom durations. Ratio also has a facility to multiply two ratios together. So in this example, I'm saying I want a duration called days, and that days is exactly 24 hours. And that's how you say 24 hours. And this just creates a new duration type named days. You could also spell it this way, and it means exactly the same thing. It's actually the exact same type, just ratio 86,400. There's really no huge advantage to one way or the other. It's more of a stylistic choice. And this custom duration of yours is a first-class citizen in the library. You can use it with the standard threading API to say sleep for a day, or if you're really tired, you can sleep for a couple of weeks, whatever you need to do. And for time points, the de facto for system clock is that it's counting time since 1970 New Year's in UTC. That's not specified, but all three implementations do this. And here's how you might say, okay, I've got my system clock, truncate that down to seconds, and I want to find out how many seconds it's been since the epoch. And this is how you would get that information out. If you want to find out how many days, you could truncate it down to days. And sure enough, this is actually today. It has been 17,007 days since the epoch. So you can use chrono to find out these wonderful, fun-filled facts. So in summary, chrono is based on three modules, say, duration, time point, and clock. Compile time errors are stressed over runtime errors. The generated code is as efficient as you could have handwritten and possibly even better. And the library is very feature-rich, but you don't pay for features you don't use. Finally, this library was designed a decade ago. It was voted into C++11 in 2008. It's been standard C++ for half a decade now, so this is not bleeding edge code. This is best practice. If you want to see time computations based on bleeding edge code, please come to my talk tomorrow at 4:45 p.m. and we'll talk about a library that does not obsolete chrono. It builds on top of it and makes it even more powerful and easy to use. I think we've got maybe 5 minutes for questions. Yes?
So you said a few times that de facto the system clock is 1970. I'm sad to report that while that is correct right now, VC is planning to change that to 1601.
No kidding.
Yeah, we'll still be UTC, but the OS gives us 1601, and we were having to do addition and subtraction. Mm-hmm. And now we're just like, yeah, we're just going to store it unchanged, and if you use 2 times T, then we'll do the 1970 adjustment.
Yeah.
So
yeah.
I'm sorry I'm breaking your slides.
Yeah, that's all right. It's thank you for the information. I can, whatever you do, the code I write can adjust. Um, it wasn't really a question. It was more of a remark that Visual is going to change their epic from 1970 to 1600, January 1st, 1600, right?
Yeah, 01.
1601.
That's NT. That's what Windows NT uses.
Yes. Yes.
Yeah, I think you forgot to mention that there's also another clock that is their high resolution clock that gives you the smallest tick possible compared to the system clock and steady clock.
That's true. I did have a slide on that. It's in there. It turns out that in practice, it's always a typed FD, either steady clock or system clock.
Okay.
Yes.
Are there any like 3D printing features in Chrono that helps with time logging?
No. Come to my talk tomorrow? Yes. and that's about an open source project that you can download, MIT license, free to use, no cost, very easy. Yes.
Tomorrow we'll also hear about time zones.
Yes.
That was the third of my question. Calendars, leap seconds?
They'll be talked about tomorrow in detail, painful detail.
Could you please repeat the comment?
Oh,
We can't hear.
I'm sorry. They were asking about does Chrono handle leap seconds, time zones? No, it does not, but I'll be handling that in my talk tomorrow. Yes.
So for steady clock, what are the requirements if a computer goes hibernate and those other things? Or is it monotonically incrementing but doesn't handle those cases?
It's kind of a Q of I thing. The question is, what are the exact requirements on steady clock, for cases when the computer goes into hibernate mode or something like that? The intent is that steady clock is as steady as possible to a second per second, so that when the computer woke up, it would take into account the seconds that it's been sleeping. I don't think the standard actually requires that. It's kind of a gray area. The hard and fast thing is it can never come back and it can never decrease in time. Yes?
So if the epoch is different from library to library, is the code still going to be portable?
The question is, will your code still be portable when there's all these details differing from library to library? Which code are you talking about? The code you write, the code I write?
So, well, for the system job, for instance.
Okay, so any code that is written that depends on the epoch of system clock will become non-portable when Visual changes their epoch. My date time zone library is dependent upon such things, and it will be portable when they create that. I'll just if-def it and as needed.
And if you use 2 times T, that's 1970.
Two time T, yeah. But Stefan was saying if you use 2 times T, that'll always be 1970. That will also always truncate you to seconds precision.
So when is this change happening?
The change that Visual is going to make in their epoch will be happening within the next release, and I don't know when that is, and I doubt Stefan will tell us.
Unspecified. Yeah, we can mess this up in different versions.
Right. So that the epoch of both system clock and steady clock are unspecified by the standard. I would call them part of an implementation's ABI, but they're allowed to make it anything they want. Yes?
When you're handling time in C, you have both time T and struct Tn, where you can break it down and have hours and minutes and so on. Is there any sort of equivalent to that to get? Do you have to sort of manually get this many hours plus this many minutes plus this many seconds?
So the question is, are there, I'll summarize a little bit. Correct me if I summarize wrong. The question is, are there field types like hour, minute, second, year, month, day in the Chrono library? The answer is no, but come to my talk tomorrow. I'm selling that hard, aren't I? Yes?
Excuse me, is the library that you're proposing tomorrow also standard later, or is it just going to be right now an abstract library that may or may not go into the standard?
The question is the library I talk about tomorrow, will it go into the standard? And the answer is nobody knows. It will be proposed. And that's all my time, and thank you very much. And if you have any more questions, find me in the hall either after this talk or throughout the rest of the week. Glad to answer them.